Welcome back to Valiant PE. Today's topic, hardness and hardenability of steel. Let's go. All right, like normal, we're going to jump straight into an example, but instead of solving it immediately, today we're going to talk a little bit about the question structure, the difference between hardness and hardenability, and then we're going to come back and we're going to find what is our answer here. So let's read the question first. Before we do that, let's do our ritual before we start a new question. Do anything you can do to give yourself a mental break between each of your 80 questions. All right, so here we go. Which of the following attributes has the greatest effect on the hardenability of steel? Rank from the greatest effect to the least effect. I'm not going to read all four answers, but basically you've got carbon content, alloying content, section thickness, and prior austenite grain size in a bunch of different combinations. So let's talk about what type of problem do we have here? We have what we're going to call a qualitative problem, which means there is no math or no numbers given in the problem. It's the toughest question type for this reason. I'll explain why in just a second, but what the test examiners are doing here is they're asking you, do you understand the concept? Do you have enough grasp of it where you can talk about it? Anyone can fake their way through a math problem. Like, the biggest mistake that people make approaching this exam is, hey, I'm an engineer, I'm good at math, I don't really need to prep all that hard outside of doing exam questions. Well, that's not true. The exam specs are very broad. If you look at the list of items on there, there's hundreds of topics. If you aren't familiar with them, there's no way you can answer a qualitative problem. The test authors can ask about anything. I mean, anything. And so the only way to prep for a question like this is to read the supporting material. That is the only way. It's unglamorous, it's boring, but you have to read your textbooks. You have to read MERM. Google will help. It's reading. And this really is what I think deters people from tackling the studying part of this exam. But you don't have to be a PhD in each of these topics. I really think all you need to be able to do is explain it in your own words, and that's good enough. There's too much on here to really know in depth. You just got to be able to speak about it briefly. And so let's go look at this problem from that perspective. I think what the question examiners are getting at here is, what is the difference between hardness and hardenability? So hardness is the resistance to plastic deformation by indentation. Resistance to plastic deformation by indentation, which means you take a sample and you stick it in a machine and it sends some type of penetrator down onto the surface, and however far it goes is a measure of its hardness. So it's a measure. So we're thinking Rockwell hardness here. We're thinking Vickers, Brunel. It's a measure. Okay, we're pretty familiar with these as concepts. Hardenability is different. It's the capacity of steel to be hardened by rapid quenching. Now, another way to restate this would be, think about how deep or how far into the sample does the hardness go when you quench it. So hardness and hardenability may still seem similar. Let's go through an example that might illustrate it a little better. Let's say I've got two steels, both of the same size, same shape, and one's composition A and one is composition B. Now, I'm going to heat them up, both above their A1 temperature, and then I'm going to stick them in a special machine called a Jominy Quench hardness tester. I just drop it in the little holder here, and then I start blasting cold air or cold water up from the bottom at a certain temperature for a certain time, and then I let it cool off and I pull it out. So this is called Jominy Quench hardness machine. Really, Jominy Quench is all you really need to know. That's the key word. You can go read about it on Google. That's not the point of this video. Once I get them both out and they're cooled down, I'm going to come and I'm going to machine a flat on the side of these samples here. And then I'm going to take hardness readings at 16th inch increments all along the length from the quenched end away. I think the test goes up to 2 inches, so you get 32 readings, something like that. The point is, I'm taking hardness readings. So now I have hardness readings at a distance from the quenched end, and I can plot them. And I can actually plot them for both steels on the same graph. And that's what I've done, so let's take a look at it. All right. Notice that the maximum hardness of steel A is higher than that of steel B. But the hardness for A drops off very quickly, where the hardness of B has a much shallower rate of change. This is a visual depiction of hardenability. Steel B has a higher hardenability than steel A, even though the max hardness of steel A is higher. So see how they're not the same thing? All right, let's move on. Okay, so let's talk about what determines hardness and what determines hardenability. The first thing is both of them are a function of cooling rate, which is why cooling rate is not an answer choice. The only way to harden steel is by rapid changes in temperature, quenching or something like that. So you have to have a cooling rate, but not an answer choice. Carbon content, however, is the primary factor in determining maximum hardness. Primary factor for maximum hardness. So, keyword there, maximum hardness. Alloying content has only a minor effect. Meaning alloy content doesn't really make a huge difference in determining how hard at an individual measurement you can get that steel. Section thickness, meaning how big the sample is. As your sample gets bigger, your cooling rate will become slower, and the slower your cooling rate means the less martensite that you will form. Martensite meaning the hardest phase of steel. Martensite is what we want when we're quenching. We're looking for the hardest phase we can get. We haven't talked much about alloying content yet. So previously, we've talked all of these are what determines hardness. Alloying content is the primary factor in determining hardenability. Alloying content is the primary factor in determining hardenability, and I'll explain why. There we go. All right. So alloying content, hardenability. Carbon content, max hardness. All right. Let's explain the difference here. This is a continuous cooling diagram for 0.8% carbon. A couple things I've got here on the bottom. I've got time in logarithmic scale, and on the left I've got temperature in Celsius. This line here is called the A1 temperature, or above this temperature I'm going to have fully austenite as the steel phase. And this is my martensite start line, meaning once I get below this line, I'm going to start forming the martensite phase. And then I've got these two lines here in green, which are the perlite start and perlite finish lines. And this graph, first of all, this is a general. It's not a specific graph. It's here to illustrate the concept, so if I'm a little off on numbers, it's not a huge deal. But this graph shows us, at given cooling rates, what phase of steel will I form. So let's draw some cooling rates. So just in the Jominy and Quench hardness test, I'm heating above my A1 temperature, and I start to cool. So let's say I've got a cooling rate that looks like this, okay? So a couple things happen here. I've gone through the start and through the perlite finish lines, and I'm at room temperature. In 10,000 seconds, I'm going to create perlite. Now, I'm going to do another sharper cooling rate, something like this. Again, I pass through the perlite start line, but I don't go all the way through, so I'm going to get some type of mixture of perlite and something else. Now let's say I do this. I cool very fast. this is what we're going to call the critical cooling rate. And it says that I have not crossed the nose of the perlite start line, so I'm not going to even start forming perlite, but I have crossed my martensite start line, and I am going to form martensite, at least some, which is the hardest phase of steel. So you might be asking, like, well, what does this mean? What's the deal? What's the matter? I don't care. Let's look at another continuous cooling diagram for a highly alloyed piece of steel and see what happens. So I've copied the same cooling rates. So these are the exact same cooling rates from the previous diagram, or very close. And I want you to notice that the perlite start and finish lines have shifted to the right. Both of them have shifted to the right. This is what alloying does. So it permits me to have a much shallower critical cooling rate. So alloying takes this portion of the curve, shifts it to the right. It essentially retards perlite formation, which means for a slower cooling rate, I can still start to form martensite. This is what alloying does to hardenability, and this is a visual depiction of what hardenability is. So there you go. Let's go back to our question and take a look at, well, hey, what's the answer? Rank from greatest effect to least effect. Well, we can eliminate A and C because we know carbon content is not the primary factor in hardenability. And if we're going to guess between either of these two, it's going to be B, alloying content. There is our answer. All right, guys, look, that's pretty much it. Let's quickly recap. We covered a lot of stuff here. All right. Qualitative problems are the hardest by far. There is no replacement for reading. You've got to do the boring, unglamorous work, but if you can explain it in your own words, you're going to be good to go. And hardness is not the same thing as hardenability. There you have it. Remember, you don't have to be a genius to pass this exam. See you next time.